Hello, everyone. Welcome to Fresh Concrete. I'm delighted to welcome you to what is the last of this year's events in the Fresh Concrete series, and that's a collaboration between the Concrete Centre and the Building Centre. My name's Elaine Toogood. I'm Director of Architecture and Sustainable Design at the Concrete Centre, and I'm going to be hosting today's event. And just in a minute, I'm going to be introducing you to our speaker. If you're not aware, this is one of a series of events that have been running for 3 years, and they're created to share just some of the wide-ranging innovative practices, new types of concrete, and emerging construction techniques, all using concrete, making concrete to primarily addressing climate change, either through mitigation or adaptation or both. So essentially technologies that bring a fresh approach and a fresh thinking to the way that we make and use concrete. So hence its name. So today's talk is called Electrifying Cement Production to Avoid Carbon Emissions. It's going to be presented by Greg Williams. He's Vice President of Product at Sublime Systems, and Greg will be explaining the principles of this new technique for manufacturing low-carbon Sublime Cement, its potential use and benefits, and the current scale of production in the United States. So Greg is dialing in from Massachusetts. So Greg, actually, if you could switch on your camera and start sharing your screen, I'll stop sharing.
Absolutely.
And there you go. And while Greg gets his slides sorted out, I will remind you that while we're on, there you go, perfect, that looks great. Welcome, Greg. So there should be some time for questions at the end of the session as we're going along. So please put your questions in the Q&A box at the bottom, and I'll endeavour to ask as many as I can at the end. And just before I hand over to you, Greg, I just wanted to say that clearly cement is one of the main focuses of attention when people are looking at decarbonising concrete. There is an enormous amount of innovation going on within this field, and but very pleased to welcome Greg to talk about Sublime Systems' particular niche of or avenue that they've been looking at and developing. So over to you.
All right. Thank you, Elaine. Very excited to be here today, and just want to say thanks to the MPA and the Concrete Center for the opportunity to get connected to folks on your side of the pond. So today I'm here to give you an overview of how Sublime Systems is reinventing cement manufacturing to help address the climate problem. So let's get into it. All right. Now, I doubt this is new information for anyone attending, but just worth quickly reiterating as it frames why the company was founded. Cement manufacturing today, roughly 8% of global CO2 emissions. That's roughly the same share as from private cars and trucks. For every ton of cement produced, about a ton of CO2 is released. And the demand for cement is growing with our urbanizing and developing population. A couple of mind-blowing stats projected that we will need twice the buildings by 2060 that we have today globally. And this is the equivalent of building a New York City almost every month for the next 40 years, which is fairly mind-blowing. So Sublime Systems was founded to have a swift and massive impact on global CO2 emissions by reinventing how cement is made. And so today we'll talk through how we plan to do that. All right, so Sublime originally spun out of a lab at MIT, the Massachusetts Institute of Technology. The initial tech was basically using electrolysis. So using a pH gradient, you have an acidic environment and a basic environment, and using these environments to drive chemical reactions, specifically dissolution and precipitation, to create cement ingredients. And so that was about 4.5 years ago. The company was founded in 2020. So that was the origin of the company. And so our breakthrough at a high level is an electrochemical method of manufacturing cement. Does not require carbon capture. We have a path to achieving cost parity with today's Portland cement when we achieve scale. It's designed to be a drop-in replacement for today's Portland cement, and it's a globally scalable process. And so we'll talk a little bit about each of these points. So we'll start with a look at a high level of how we're different from traditional cement manufacturing. So with traditional cement, look at the yellow box in the upper left. You mine a bunch of limestone out of a quarry. That limestone, you take some sand and clay, throw it into an enormous rotating kiln. You heat that kiln up to about 14 or 1500 degrees Celsius. This is typically done by burning coal or natural gas. And what is produced out of that process is clinker. That clinker is ground with some additives to produce Portland cement. So there are really two main reasons why this process is so CO2 intensive. Number one, limestone, when it thermally decomposes inside the kiln, it releases roughly half its weight in CO2. So that's source number one, is it has all that CO2 trapped in the rock. The second source is the burning of the coal and natural gas. So Sublime's way of making cement, we address both of these. Number one, we don't use fossil fuels. It's powered by carbon-free renewable energy. And we also don't use limestone as a feedstock. We use non-carbonate materials that don't have CO2 trapped in them. And so this process is powered, as mentioned, by renewable energy, and we produce two main ingredients, a lime and silica. Those are blended with some other ingredients to create Sublime Cement. And then everything to the right is the same. So it is designed to store in a silo the same, ship in a bulk truck the same. There's no custom pneumatics required. It batches, pumps, places, finishes the same. And then when you hydrate it in concrete, it forms the same calcium silicate hydrate, or CSH, that you find in concrete made with Portland cement. So this is just a look at the process at a slightly lower level. So let's talk about feedstocks. So as mentioned, we use non-carbonate feedstocks. These can be calcium silicate rocks, such as basalt, which are very prevalent in the Earth's crust. We also can use a variety of industrial waste products, such as slags from steelmaking or recycled or returned concrete fines. So these feedstocks are digested essentially by the Sublime process, and then we sequentially pull out the individual components of the mineral feedstock. And so any elements that are not useful in cement chemistry, such as iron or magnesium, those are removed. They're also purified as part of that process. They can actually be turned into other co-products for other industries. For example, iron oxide pigments for building materials, or magnesium hydroxide can be used in wastewater treatments and other chemical applications. But the two main ingredients, as mentioned, that are produced are a hydrated lime, calcium hydroxide, and a reactive silicate. These are produced as free-flowing powders. They're then blended together with a few other additives, and that produces Sublime Cement. Now, one other call out, we actually produce an excess of the silicates compared to what we need for just the cement. And so we intend to sell those silicates as a standalone SCM. So they make a very performant reactive SCM, can be used similarly to a fly ash or a high-end natural pozzolan. So our philosophy is really use the whole rock. So there's very little waste from the process, and we use the majority of the composition of the feedstock. So this approach is actually fairly similar to Roman cement. So back in Roman times, they would heat limestone, mix it with volcanic ash from Mount Vesuvius to create concretes. And some of those structures still standing over 2,000 years later, so we know it makes durable concrete. So speaking of durability, so we've conducted an extensive suite of durability tests. Our kind of test suite is always growing as we learn about new tests that customers and partners care about. But we've gone through these with the initial version of Sublime Cement. These are mostly kind of all of the key tests from ASTM, and also AASHTO, which is the equivalent of ASTM in the US for highways and infrastructure, but tests for alkali silica reaction, or ASR, chloride permeability, sulfate attack, kind of all the most of the main causes of degradation of concrete. And in general, The material outperforms the Portland cement controls. We always run controls when we do these tests. And the ones that are shaded in dark green perform significantly better. So it makes very durable concrete. It's kind of the takeaway. So in terms of looking at the effectiveness and scalability of new solutions, there are a couple of important things to consider. Number one is minimizing total embodied energy. Is the process energy efficient overall? Number two, given there's a lot of demand for clean energy coming onto the grid, are we using that efficiently to reduce CO2 emissions? And third, cost. Are we the lowest cost of CO2 abatement? So this just gives you a quick snapshot of how does the kind of energy, the embodied energy rather, of Sublime Cement at scale compare to kiln-based cement manufacturing processes, from the least efficient wet kilns to the most modern efficient kilns deployed today, both with and without carbon capture. So at scale, it has the potential to be significantly more energy efficient. Now, with the clean energy coming onto the grid, there's a lot of things you can do with that to reduce carbon emissions. You can charge a battery in an electric vehicle. You can power a heat pump to replace a natural gas furnace. You can power a direct air capture plant. Now, Sublime Cement provides, let's say, more leverage than a lot of these other electrified technologies when you just look at a pure CO2 avoided per green kilowatt hour consumed. And then there's finally cost effectiveness. So there are a number of different ways to potentially mitigate CO2 emissions from cement manufacturing. We like to use an analogy of a leaky tap. If you turn on a tap and the water flows over the sink onto the floor, you can, number one, mop it up, which is the equivalent of direct air capture. It's the least efficient. You can, number two, put a bucket under the tap or install carbon capture, or you can turn off the tap, which is Sublime's approach, where we avoid emitting the CO2 in the first place. And this is definitely the most cost-effective approach. So we know that it's a conservative industry for a lot of good reasons. We don't expect anyone in the construction industry to take our word for it. We have worked with a number of third parties to validate our technology and our approach. Our compliance with ASTM C1157, which is the performance-based standard for hydraulic cements. This has been validated by a third-party accredited lab. We've also had a life cycle analysis done of our process engineering models. This is basically the equivalent of a preliminary EPD, confirming our pathway to over 90% reduction in CO2 emissions at scale. And we've also had a safety data sheet created confirming that Sublime Cement is no more hazardous than typical Portland cement. So to achieve our mission of both a swift and massive impact on CO2, we know we have to scale quickly. So to give you a sense of where we are on our journey to scale, as mentioned, we spun out of MIT in 2020. We were basically producing gram quantities of material on a lab bench. We now have a pilot plant that is operating here outside of Boston. It has a nameplate capacity of about 250 tons per year. We're using this material for field trials with potential off-takers, which I'll talk a little bit about, as well as evaluating equipment for commercial scale plants. This plant's fully automated. We've achieved over 1,000 hours of continuous operations. And then the next step in our journey will be our first commercial scale plant. So this will be located in central Massachusetts, about an hour and a half from Boston. We have site control on a piece of property. It's being cleared and graded in preparation for breaking ground early next year. And we plan to commission this facility in 2026. So the primary purpose of this plant is to show that the technology can scale to commercial volumes cost effectively. But that's still a relatively small plant in the grand scheme of cement manufacturing. So to achieve our mission, we have to get to true industrial scale. These are megaton facilities, 1 million tons a year or more. And we plan to have our first megaton plant online in 2028 about. We're going through an extensive siting exploration right now, looking at both the EU as well as North America for potential sites, and expect to have our first site identified by the end of this year. Our plan is then to bring several full-scale facilities into development simultaneously, so that we can go after that swift and massive impact. This is just a couple of pictures of the site in Holyoke. It's a former industrial site. It's an old paper mill town. Paper mills have all shut down, but there's already some pre-zoned industrial properties. It's right on the Connecticut River next to a hydroelectric power plant, which is great for us in terms of plentiful source of cheap, clean energy. Recently, it was announced that Sublime, we were fortunate enough to be selected for award negotiations with the Department of Energy for a grant to help construct this plant. So that will definitely accelerate this milestone, and we're very, very grateful for the support. So we're excited to get construction started next year. So I wanted to talk a little bit more deeply about how we have worked with some of our value chain partners to evaluate the material in the field. Because, I mean, ASTM compliance, it's one thing, but you have to show material works, let folks get their hands on it. And we recognize that the concrete producer and the folks that place and finish the concrete, they are critical gatekeepers for new materials entering the market. You know, their recommendations are heavily weighted by the rest of the value chain. So our strategy has been to develop close partnerships with a number of these folks across the country. Now, given our location in the Boston area, we are furthest along with those relationships in the Boston and New England area. We've worked very closely with one particular provider, Boston Sand and Gravel. This company's been around for over 100 years, very well-respected, innovative producer in the Boston area. And we went through a 4-phase material validation process with them. So starting with letting the partner test the material in their lab, they took their typical 4,000 PSI mix. It's a mix of about 80% Portland cement, 20% fly ash. They basically did a 1-for-1 swap, replaced all the cementitious material in that mix with Sublime Cement, and then tested it in their lab. They saw that at 28 days, we outperformed their benchmark mix by about 20%. Now we know that concrete is very regional. Materials vary from area to area. So we are repeating this process with a number of other partners in different regions across the US. So to be the true drop-in replacements, you know, it's not just how the material performs that matters. It actually needs to feel similar. So it needs to set and finish similarly to avoid slowing down the job site or, you know, tiring out the shoulder of a finisher who's working the material. So next we brought in some veteran finishers, folks that have been doing this job for over 30 years, to do some finishing trials on some mock-ups. We then batched some larger batches, did a truck trial batch to see how does the material perform in a larger batch, how does it retain slump when you are in transit to the job site to make sure it's still workable. And this basically showed that the material characteristics, they were consistent in larger quantities, and you could get to the job site with workable material. And then lastly, we did our first field pour. So this was back in January of this year, I believe. And we started with baby steps, did a small portion. It's just a mud mat, which would be then covered up by a foundation. It was a brutally cold day, really put the material through its paces, very cold and windy. We pumped it and placed it. It pumped, it set even in these tough conditions. So that was considered a big success for a first pour. We then did a topping slab inside the lobby of what will be the greenest office building in the northeastern United States. This was a polished lobby slab. So we went through the full finishing cycle on that material, had a chance to check, you know, how do we comply with the desired job cycle of finishers and the overall project. And it's a very cool project. You walk over the lobby, there's a little plaque embedded in it. So it was a neat pour. And then just a few weeks ago, we did a sidewalk. So this is our first outdoor pour, our most sophisticated mix design yet, you know, lower water to cement ratio. It had fibers, it had superplasticizer as well as hydration stabilizing admixtures. Basically we recognize we need to test the material in a wide variety of conditions and kind of progressively build confidence across all general use applications. So we will continue raising the sophistication of our field pours. and also go through the same process in other regions. So many more exciting projects to come. And just to wrap it up, we were fortunate enough to build a fantastic bench of advisors with extensive experience in structural engineering, construction material manufacturing, cement and concrete academia, business development. So we've got a lot of help. We rely on these folks to pressure test our work and make sure we're making good decisions. And then lastly, this is our leadership team. So our two co-founders, Dr. Leah Ellis and her former academic advisor, Professor Yet-Ming Chang, founded the company. And we have over 200 years of cement, concrete, and construction experience across the leadership team. So it's a very mission-driven team and a great group to work with. I've been there about 1.5 years now. So that concludes the prepared presentation. I thank you once again for letting me get some time with you, and we'll hand it back to Elaine.
Fantastic. Thank you very much. Thank you very much, Greg. That was really interesting. And I learned a lot there, even though we'd had a chat in advance. So that was great. Now, I think we had a very slight glitch right at the end of that for some reason. I think we could hear you fine.
Okay.
Listening heard that. But what it did mean is that I've lost the direct link to all of the questions that were asked. So, but I've been looking at them and I've remembered most of them. So I'm going to ask you the questions anyway.
All right.
And maybe if people have some more, they can reapply them in the Q&A.
All right, we'll do our best.
Yeah, exactly. So now that's brilliant. They're coming through. Thank you very much, everybody. So there was lots of great questions, and one of them was related, or a few of them are related to the way in which the concrete is used, and it's great to see that you're trying it in a few different situations. What about the early strength gain? Because that's sometimes an issue there. How does that compare to PC, say, or what were your experiences in that regard?
Yep, no, it's a really good question. And the kind of the story on pozzolanic cements, which is basically the foundation of this and what Roman cement was, is it's a little bit slower hydration reaction than Portland cement. And so you get tremendous long-term strength, 28 days and beyond. Typically by 56 days, we're significantly exceeding the strength of Portland cement controls. It's very durable, non-permeable. But it does take a bit longer to develop strength. And so it is today, we're on version 1 of the product. This is going to be an iterative product development process like it is for any product, whether you're talking software or hardware. It is already applicable and performant enough for many applications. That would not include like precast right now, for example, where you need to develop, 3,000 PSI by 12 hours or something like that. Or perhaps, vertical construction elements where you have to flip your formwork every 24 hours. So we have a path to addressing that. It will be a true general use cement. But it's going to take us a little bit of time to get there. That's the main focus of our R&D efforts right now. We have some very interesting kind of development work streams that are looking at tools to boost that early strength. So I have high confidence we will get there. We're just not there today.
Okay, so that's something. I mean, there's always, nothing is ever going to be a complete like for like switch.
Not your first swing at the plate, for sure.
No, exactly. So in the use of this, has there been any investigation or looks of using your cement with SCMs? Or is the idea that so for example, there's a lot of interest in calcined clay at the moment going forward as a sort of long-term solution, but any of the others, that are evolving? Obviously, you said already that could be based on RCP, which is a potential SCM as well. Do you want to talk a little bit about that?
Yep, absolutely. Yeah. So it is designed to be a drop-in replacement for cement. And so that means it would replace all cementitious material in the mix. Therefore, you would not need to use an SCM such as fly ash or calcined clays and still be able to achieve the same or greater levels of decarbonization. That being said, we get that question a lot. And so we have done some testing. In fact, we've had a few of our ready-mix partners test it in that model as an SCM. It works. It works better in some situations than others. It's not kind of our main focus of deployment. Right now, it's the cement, and then, as I mentioned, the silicate can be used as a standalone SCM, and that is something that we're putting a lot of time into, is doing concrete testing with just the silicates to show performance and durability in concrete. So those are kind of the two main products applications we're thinking initially, but since we do get that question a lot, I think we'll further explore whether the cement can be used, as a partial replacement as well.
Fantastic. Thank you. And what about impacts on water use? So water cement ratio, what's it there? And also with that as well, long-term durability and exposure. So what sort of testing have you looked at for that point of view?
Yep. Yeah. So we have those. First of all, we've done compressive strength testing, 3-point curves at a wide variety of water to cement ratios. The actual field trials, the deployments that I walked through, those were done, I believe, from a 0.45 to 0.50 water to cement ratio. So in a somewhat narrow band, we are looking to kind of expand that band in future deployments. But yeah, the idea is, you would be able to use it in just as wide of a variety of mixed designs of water to cement ratios as effectively as Portland cement today. Yeah, durability is definitely one of the strong points of the material. One other point just on water usage, which I know isn't what you were asking, but we get asked a lot, which is about the production of it, is like, how much water does production use? And so it uses less water in the manufacturing process than Portland cement if you include carbon capture, which is kind of our benchmark. This is how we think of that as our main competitor, is traditional Portland cement manufacturing with carbon capture tacked onto it. And so we consume less water than those processes.
Okay, I guess it depends on the process as well, doesn't it? That they're using.
Yes.
Yeah, of course. Okay, excellent. So there, I've been forwarded all the questions, so I'm now going through this. There's quite a lot of them here. There's quite a lot of stuff about so we talked a little bit about the making. So what about then the concrete when it's made? What about fire testing? Has that been carried out? And what about, and you mentioned safe. Yes, I'll answer the fire question first. Have you managed to do that? Yep.
Yeah, no, we have not. No, there's a lot of tests that need to
A lot
be
of hoops.
and given we're not, at the scale we are manufacturing at today, no one's going to be using it for complete structural elements and high rises or anything like that. So like there's a prioritization of the tests that we're doing today.
Yes.
But no, not yet.
Yeah. Okay.
We'll
No,
get
that's
there.
understood. Yeah, exactly. And it's a step. Innovation is a step by step, isn't it? And it's about proving and then moving on to the next stage. Yeah. And on that question, there's people are saying, looks great. When can we have it? When's it going to be available? Is it in the standard? And of course, not yet is the answer to that. Yeah, a few steps to go through. Yeah.
Yep. I wish we could get it out to everyone today, but yeah, it takes some time to build cement plants, unfortunately. So
yeah. Well, and I guess one of the other related questions then is in terms of the rate of productions, which is of course linked to scale. But is this a similar time frame for a manufacturing process of the cement?
oh, you mean in terms of like the
Actually,
dwell
throughput.
time, so to speak, of the
Yeah.
material?
Yeah.
Yeah.
Somebody's asked a question specifically about that. I don't know if they meant scale, but they are specifically about rate of
it's
production.
great. I mean, I wish our head of engineering was here to give a better answer, but it certainly isn't today because it's kind of a multi-step manufacturing process in the pilot. So it takes longer to produce material. When it's at scale, order of magnitude, it's the same. Not a lot higher, not a lot lower in terms of how long it takes to go from feedstock coming in one side to powdered cement coming out the other side. At order of magnitude, it's not that much different.
Okay, okay, good. And there's another question here, which is very much ticked into the sort of circular economy aspect of it. So you mentioned that there's little waste produced, and you talked about, but when you start to then scale up, um, there's a question about, you know, how much of that waste is produced and the use of it then for you able to talk a little bit about that? I think you did talk about there being byproducts of being possible. I don't know whether then there's waste in addition to those byproducts.
Yeah, yeah. So in terms of overall environmental impact, I mean, we talked about the CO2 reduction potential. We've talked about water usage. It does consume, and our process consumes more electricity than Portland cement production because it's completely electrified, but it is a similar amount of total energy. And then at scale, we believe we have a path to bringing that down significantly such that it requires less energy overall. There are lower particulate emissions, lower acid gases like NOx and SOx emissions. So overall, it's a more environmentally friendly process. Another point is, traditional Portland cement, to get to the quality limestone that is required, there's a lot of waste that is generated in that coring process. You have to dig through a lot of tons of limestone sometime to get to the material that will work. Also, since that's half CO2, that's a lot of extra weight that's having to be transported to the site. We don't have either of those problems. We are less sensitive to the quality of the feedstock because of our process, and we don't have to ship all that CO2 around the world trapped in rock. And then to the circular economy point, I mentioned that we can use waste products as feedstocks. That's definitely a less mature area of our technology. We actually just got another grant from the Department of Energy to further develop our electrolyzer technology focused on the circular economy. So basically consumption of waste feedstocks. That is things like municipal solid waste, steel slags, and that includes electric arc furnace slags, which don't produce cementitious slag like blast furnaces did. So when that technology gets folded into our process, that will really boost the kind of overall circular economy benefits.
No, so it's an interesting point that there's a few things you've raised there. You might see me pull a face, but it is interesting as the cement manufacture is sometimes different in different parts of the world, and yeah, and so there's yeah, the stats are very different in the UK with
Oh yeah,
regards to that. Yeah, no,
yeah.
and in fact, actually, that was one of the things I did want to raise is that we often see that point about cement is a ton of carbon, and in the UK, it might have been a while ago, but actually, latest figures is the average is actually closer to 810 kilograms, and it's coming
Yeah.
down all the time. So yeah, that's that's not to say, but it is for people listening in, it's really important because there are national differences, and actually sometimes solutions are the way that you're talking about it, but all the stats that you use will be very different in the different contexts of how things are made and sourced. But
Yeah, you guys
yeah.
are, no, absolutely. And I mean, Europe in general is much further ahead in production of blended cements and driving down that kind of CO2 footprint than we are in the US. So this is,
Yeah.
you're right, tailored at more of a North American audience. So
Yeah, no, that's fine. I just wanted to make that clear for the audience listening in. That's yeah, that case. Okay, no, that's fantastic. So listen, I think we're going to need to call it a day. There are a lot more questions. A lot of them very similarly related to other ones about scalability, a cost, obviously. But are you able? I mean, you're going to say it's comparable, or
yeah,
you know,
so yeah, I
hard
was
to say right now, isn't it?
Well, I was waiting for that question. I mean, when we achieve scale parity, we believe we can achieve cost parity. I mean, even our plant in Massachusetts that we're building in 2026, 30,000 tons a year, that's roughly 3% of the size of a typical cement plant. If you had a Portland cement plant that was that scale, it also would have to sell at a significant premium. So yes, there is a bit of a scaling premium with the material to help us cover those costs until we get to scale. But we do believe we will achieve parity or even beat it.
Yeah, excellent. And actually, there was a couple that I should pick up because a few people have mentioned this. It was when you're talking about the reuse of other materials going into, there's always there's that safety issue that people are concerned about in terms of what's being used, end of life, dust. Is that sort of those sorts of tests started to happen yet? But presumably you've got a team looking at that, or who what's the if people wanted to follow up on that specific issue, who would be what area of your team do they contact?
Yeah, so we have a dedicated safety team, and then our engineering team has extensive background in building industrial scale chemical facilities and solid handling facilities. We have folks that have worked in the cement industry. We have folks that have built, chemical plants. So it bridges both our engineering function as well as safety that is integrated into everything that we do. It's number one, both in the office, just every day, as well as thinking about designing of plants for future workers. And that is a big part of the just kind of screening criteria that we had to go through to get the grant that I spoke of from the Department of Energy. We had to have a very extensive safety plan for the folks that would eventually be working in the facility.
Okay. Fantastic. So, on that note, which of linking to the rest of your team, I would say thank you for your time, and then you're going to need to get back to working with them to present it. Your website is all online, so if people wanted to follow up, they'd be able to send in a general query to that, wouldn't they? So, I just wanted to say thank you very much. It was been an excellent talk, and what a way to end our series. I'm going to just share my final screen here, which hopefully people can see. Can you see that now? Yeah. And just to remind people that to thank you, Greg, thank everybody for listening in, and to remind people that as this is the last of the event in this year's series, but you can catch up on the 15 recordings are available that we've had over the last 3 years of Fresh Concrete, and they're available if you go to the Concrete Centre, Fresh Concrete, and also with the link is on the screen, but also through the building centre as well. We'll be hosting these different recordings. So thank you very much, and I wish you all a good rest of your day. Thank you.
Thanks, Lane.